Hello everyone. Rivers. Let's talk rivers today, including the basics of rivers, the drainage patterns that rivers follow along the land surface, the processes rivers take, including weathering, erosion, deposition, the courses of the rivers, including the upper part of the river and the lower parts of the river and the different features we have involved there. We'll give some examples, of course, of rivers, and we're even going to talk a little bit about bonus information on floods. So let's get ready for rivers. I will make a quick note if you need to um, hear anything again, don't hesitate to pause and rewind. I'm going to go move pretty fast through all this. So here we go with river basics. Here's a table showing the longest rivers in the world, noting that you can see here the Nile is the largest and longest, or actually the longest river in the world at 4,100 miles. But the Amazon comes in a quick second at 4,000 miles. And if you notice the flow at the mouth of the river here with the Nile versus the Amazon is just a monster. It is by far the largest river in the world, fielding all that rainwater from the rainforests across Brazil. But the Amazon is definitely the largest river in the world, if not the longest. The Yangtze is another big one in Asia that goes through China there. That's a really, really big one. And the largest here in the U.S., of course, the Mississippi, the largest in North America. And then I'll note down a little bit further, not as long, but definitely very, very big, the Congo River, the second biggest river if you're going to count the amount of flow. Here's a world map of the rivers, just kind of putting things in context. You got the Mississippi over here in the northern part of North America, the Congo that I mentioned before down here in the central part of Africa, and where they get a lot of rain. The Amazon, of course, all the way across the northern part of South America in that tropical rainforest area. A couple of big ones, the Ganges and the Brahmaputra coming through here through Bangladesh. That's a really big one coming out of the higher elevations of the Himalayas there. And all the river flows in Asia and Europe are seen here as well. So just to look at where some of these rivers are. About 20% of the precipitation that hits the land runs off, while 80% soaks in and becomes groundwater. We talked about groundwater a little bit, and noting that groundwater is a very significant water source, fresh water source for us. But this runoff water eventually makes it to small streams and gullies, and eventually into the river systems, the main stream and the tributaries that is. Showing a picture here of the Kishwaukee River as part of the Rock River suite and the area that the Kishwaukee drains there, including all of northern DeKalb County. A couple of features here. The channel is what they call the path that the stream follows. The headwaters are where the stream begins. The stream load is the sediment it carries. The mouth is the end of the stream, typically going into a large standing body of water. If the mouth ends up being at another river, they call that the confluence, the joining of two streams. And the gradient is the slope of the land over which the streams flow. Let's talk a little bit about river drainage. The area a river drains is called a drainage basin. Pictured here is the Gulf of, or the Mississippi River drainage basin, outlined in purple down here where you can see it. This whole area, the entire area of the central part of the U.S. from the Appalachians to the Rockies is drained by the Mississippi. You can see the picture in the top here. Any raindrop that hits in the central part of the U.S. ends up in the Gulf of Mexico. Any raindrop along this area, the Atlantic, any raindrop here, the Pacific, there's the so-called Great Basin. Any area, any raindrops that fall in here don't go anywhere except they evaporate. So that's kind of an interesting area. This is the site of an ancient lake, Lake Agassiz, that lined the area around Nevada and Utah. In fact, this lake evaporated away, leaving behind the Great Salt Flats here, the flat area This is where salt was left behind by the evaporating water. And any drop of water here, the Great Lakes, and then you drop up here, the Hudson Bay. So there you go for drainage basins. Drainage patterns are the way in which a river flows across the land surface. It's mainly the main channel has tributaries and how they roll over the landscape. It's dependent on the relief or the elevation change of the river in the area, the rock types that underlay the river, and features as well as river size. And there are four main patterns that you see out there: dendritic, radial, rectangular, and trellis, and we're going to talk about each. Here's a look at a dendritic stream pattern. It looks like what you would see on a leaf. In fact, they use the same term. You can see how the river just kind of like breaks from reaching branches all the way into the main tributaries itself. This one in Yemen, good image on Google, but illustrating a dendritic drainage pattern. Here's a radial drainage pattern, noting that it's kind of like a spoke-like pattern that forms on circular mountain landscapes. This is Mount Taranaki, an impressive lava flow that came in a very circular way through this mountain in New Zealand. You can see it's developed a nice radial drainage pattern. And here's a rectangular drainage pattern forming because of highly fractured rock landscapes. You'll see the Volga River here kind of coming and taking a right turn and going another direction based on the rocks. So very interesting drainage pattern there for rectangular. And then finally you get this trellis drainage pattern where you have these streams going one direction. You've got all these tributaries coming in to fill. And what you're seeing here is this area would be a valley, and this area would be a valley. And up here is the peak between the valleys where the water's coming from. So that's kind of how those operate in the trellis drainage pattern. Excuse me. Let's look at river processes. And these include weathering, erosion, and deposition. The effectiveness of a river at work to create weathering, erosion, and deposition depends on its overall shape and depth and ultimately the river's energy and how much power the river has. First, with weathering, we look at how rocks are broken apart in this process. The weathering process is mainly mechanical here in rivers, but also chemical as it flows through and dissolves rocks below. The chemical process would be corrosion. The water itself, rounding out rocks, would be hydraulic action, and rocks smashing into each other, abrasion. So this is a look at the weathering that takes place in rivers. The erosion is the actual picking up and moving of material in a riverbed or in a river. You can see here the difference is in the size of the particles. Traction are large boulders rolled. That really constitutes only situations where you have a very, very high energy and high flow from the river. Saltation is where pebbles skip along the bottom. Suspension are particles held up within the water column itself, and solution is the stuff that's dissolved by the water. And you can see the pictures of each here. This is how sediment is moved. That is erosion. And then we have deposition, which is how material is set down in a river. Material carried by the river is dropped, usually in areas of low energy or low speed. This occurs in places like the inside bends of rivers. You can see here the outside curve is where rivers might carve and where the river is moving faster, but on the inside curve it's where rivers are moving slower, and this is typically where you see deposition. There of course are other areas of deposition along a river, but this is just an example here. Let's talk about the river course, which includes both upper course and lower course features. The river course, when looking at it over the entire profile, oh boy, let's minimize that there, is the speed of the river and the kind of the features that dominate that area. We're going to talk upper course in its own kind of situation because it's really unique and fast moving. Usually the parts of the river that are up in the higher areas with greater drops. And then the middle and lower course are usually areas that are flattened out and have their own characteristics. So first we start with the upper course. Let's start with upper course, sometimes called younger portion of the river. Upper course features are formed because the river is moving very fast. There are steep gradients in these areas, and so the river carves out V-shaped valleys with the fast-moving water. You'll see rapids very commonly. Because the river is moving so quickly, it's got a lot of energy. It'll carry all sizes of sediment, and it rapidly downcuts, which makes the river deeper and deeper, and thus creates those deep V-shaped valleys. The bed load of rivers is typically the area that the material that's carried along the bed itself, and as you might imagine, it's really big. The bed load is really large in these upper course portions of the river. That fast-moving water can carry all size particles. You often see cobbles in addition to pebbles up in this area, and even sometimes boulders rounded out. Upper course commonly have rapids. You can see this beautiful picture from the Yellowstone River in Wyoming of the many rapids you see along that river. Beautiful place, beautiful river to go see if you've never seen it. And there, of course, are many gorgeous gorges created by these upper course rivers, including this one in the Ganges River going through the upper parts of the highlands in India. And you often see waterfalls in some of these upper course features. Pictured on the left is Angel Falls, the tallest waterfall in the world. It's almost a kilometer tall. The waterfall's a kilometer over the cliffs there in Venezuela. The Niagara Falls is the largest one here in North America, and you can see pictured there in beautiful waterfall, 3,000 tons of water going over that waterfall every second, so it's just pretty impressive. And then you've got the Victoria Falls there in Zambia, which is part of the Zambezi River, extremely large waterfall, very beautiful. You can see pictured there. And then, of course, the mid to lower course of the river has its own set of features. In the lower course, the water is slower moving, but because it has so much water volume, the channels are very wide, and so it moves a lot of water. It carries typically only the finer sediments. Because the water is wide and deep, it's not really kind of like moving very fast on that bottom like you would see in the younger or upper course portion of the river. And so you get these big U-shaped valleys with these meandering rivers bending this way and that, large wide floodplains, and typically bluffs that form on either side due to the lateral erosion pattern. Here's a picture of some meanders. These are the large bends where the river cuts into the banks. This picture in the top right here, you can see how the river flows around the outside curves of these meanders, and on the inside curves you often see deposited sediment. In fact, these meanders cut and cut and cut into the landscape until they eventually connect. And when they connect, the channel kind of moves on, and the meander that was once there forms its own little lake called an oxbow lake. So oxbow lakes are formed by the meanders cutting off from the main channel. Kind of a fun little feature there on some of these lower course, mid and lower course parts of the river. These meanders can cut deep into the rock. They're pretty powerful. Flowing water is one of the most powerful forces on Earth because of its relentless pursuit at digging into the ground. You can see these incised meanders here in Arizona with the winding Colorado River. And there's a nice picture of an oxbow lake off of the side of the Mississippi going through the central part of the U.S. And it's of note that these little sediment blotches here deposited on the inside bends of the meanders, those are called point bars. Yeah, great place to stop if you're going on a canoe trip. These little point bars are great places to hang out, and they are where the water is a little bit lower in energy, and thus deposit of sediment is made. Oftentimes the river floods, and you can see the flat floodplain on either side of the river here, where you have that nice wide, deep channel, and you've got whenever the river floods, and it typically does so every year, it floods onto this floodplain, the flat area around the river. And when it does flood, it actually deposits a lot of sediment along the sides of the river here. This sediment deposit along the sides of the river, when it floods, it builds up, is called the natural levee. And you'll see those all along the sides of rivers. Here's a nice picture of flooding, which typically rivers flood every year. Depending on the year, it can be a big flood or a small flood, but all rivers reach flood stage each year, and they don't spill over oftentimes like this, but this is a particularly large flood. You can see this area is likely very flat and wide underneath this area. This is the floodplain itself. And then you can see the natural levees here along the side of the channel, marking where the channel is moving based on when the river actually starts to flood, that low energy that it hits when it goes over the banks, it builds up that sediment or that natural levee. So that's kind of how that works. When the river actually eventually slows down, it'll deposit all the sediment it's carrying. Here's a couple of features that are depositional features from rivers. First, the alluvial fan here. The alluvium is like sand and gravel, and fan is like this fan shape that occurs when a fast-moving mountain river hits the valley floor. All of a sudden, the water slows way down, the deposits are dropped, and you get this fan shape, kind of like, you imagine somebody holding one of those handheld fans and fanning themselves like, oh my land, it's so hot. That's an alluvial fan. And then we have a delta here, shaped like the Greek letter delta, which is why it gets its name. Deltas are typically what you see building up wedges of sediment when water flows into a larger body of water. This is the Nile River delta you see in the bottom right here. Here's the Mississippi River Delta, a massive amount of sediment being carried by the Mississippi River, dumped into the Gulf of Mexico, and when that flowing water from the Mississippi hits the Gulf of Mexico, it slows way down and just like lets go of all the sediment it's holding. And so you can see the vast sediment plumes here that are let go by the Mississippi as it hits that Gulf of Mexico. And this stuff builds up. It's really heavy. It weighs down on the Earth's crust, causing it to sink down. And of course, the Mississippi River comes out here, but the Atchafalaya branch of the Mississippi comes out here, and there's lots of distributaries, like little spits of water that come and drop sediment at the end of the river. Distributaries. You can see the Nile River here, delta pictured as the Nile River hits the Mediterranean Sea. You can see here I've got in this picture the distributaries are labeled. This areas where water kind of trickles in, slows down, and dumps all of its sediment. And then here's the Ganges River flowing from high elevations up here in India down through Bangladesh. You can see the material come and deposited here. This is one of the larger river deltas in the world, some of the largest rivers in Asia there. Okay. Bonus material, floods, to end us here today. Rivers are, of course, desirable places to be around. Rivers provide sources of water, agriculture, lots of irrigation for crops. And of course, when the river floods, it deposits really good fertile soil. It's good for industry, transportation routes, energy, waste disposal, flat areas along the floodplain for construction. So lots of reasons to live along a river. However, of course, we know the disadvantage, flooding. Flooding is the most common and most costly type of natural disaster. So we're going to highlight the different types of floods here real briefly. So a flash flood is one of those floods that comes when you get a really big downpour of rain. The flooding that occurs there in the short term, that's a flash flood. The flood that occurs over days and weeks of rainfall that is just kind of overtopping the rivers, that's called a regional flood. We're most familiar with that. We'll talk about that because of the Mississippi here in just a second. An ice jam flood is where broken ice in areas that are colder form a dam of ice, and then the water dams up and kind of floods upstream. Also called upstream floods, ice jam floods. And when those ice dams break, you can have flooding downstream. This is ice dam failure. Geologic floods include things like landslides, uh, moving into an existing body of water, creating a kind of a torrent of water. Sometimes those landslides can dam up a river, and then eventually the landslide will break, causing a flood. That would be categorized as a geologic flood. You can have a lahar from a volcanic eruption where the um, volcanic material mixes with the snow caps to create these big cascading mud flows. And then subglacial volcanic eruptions occur in places like Iceland, and you get massive floods underneath the glacier. So these are all geologic in category. Coastal floods include storm surge from hurricanes and tsunami floods. And then dams that are breached, man-made dams breached, or levees that collapse cause floods as well. So these are different types of floods. I'm going to just highlight a few key points about some of these, starting with the regional floods. Regional or downstream floods occur because rain builds over relatively short periods of times, like days and weeks, and it takes a long time for the water to subside. Pictured here is kind of like a little look at the discharge in cubic feet per second of each of the rivers, major rivers in the U.S., and you can see by far the Mississippi is the largest, just a really massive amount of water coming out of the Mississippi here. And so as a result, the Mississippi River is one of the biggest risks for flood in the U.S. It is the third largest river basin in the world. It includes half of the major rivers in the U.S. The water flow can reach 18,000 cubic meters per second at its mouth, and the water flow increased fourfold during floods. Pictured here is a flooding of major interstate intersection here from the Great Flood of 1993. We'll talk about that in just a second. The Mississippi has had some historic floods. 1717 was the first large flood in New Orleans, kind of alerting people that this river means business. Levees have been built along the Mississippi to prevent future floods, and of course those fail and cause flooding. 1927 saw breached levees and flooding, killing lots of people. 1973, much of the same. You can see here though, in largest of amounts of water, the 1993 August flood was the greatest in the Mississippi. The 1993 flood was the biggest in 140 years. We had a wet winter and spring, and an even wetter summer that made much of the area around the central U.S. filled with water. And the place it's going to go or end up is the Mississippi. And so levees were overtopped and damaged by waves. We had over 1,000 levees in the upper Mississippi River system overtopped and damaged. It submerged 75 towns and caused over 10 billion in damage. And you can see pictured here a damaged levee here with water flowing over. The amount of rainfall, the sheer amount of rainfall in the central part of the U.S. that was had during that time helped contribute to this. And here's a picture of flooding of the Missouri, which is just upstream from the Mississippi's its confluence with the Mississippi here, but just massive flooding causing lots of problems. The largest flood ever to have been known, geologically speaking, is an ice dam failure. Back at the end, or toward the end of the last ice age, about 18,000 years ago, Lake Missoula, Washington here. What happened is you had an ice sheet here in Canada. It was melting. It created these great glacial lakes, and the glacial lake here had an ice dam that was built by ice. That dam right there broke. And when it broke, the water just flushed over the entire eastern half of Washington State. It created a massive flood of 17 million cubic meters per second at water going over 70 miles an hour. It actually was such a large dam breach, and I'll go to the bottom picture to show you here. This is the ice dam that broke here. It was such a large breach that it basically washed away all of the vegetation and soil from this area in the eastern part of Washington State, and now the area is like this graveyard of boulders and massive structures. That's called the channeled scablands. So that was possibly the largest flood that the Earth has ever seen, or at least in the recent past. The deadliest flood? China, 1931. From July through August of 1931, unusual amounts of rain, 7 tropical cyclones, and those were following heavy winter snowfalls. There was such high silt content in the river, so much water, that almost all the rivers in central China were overtopped. It wasn't just one river, it was like the entire region of central China. And this is a very highly populated area. 51 million people were affected by these floods. That's a quarter of the population of China. And because of drowning and cholera outbreaks and typhus outbreaks, starvation, 3.7 million people were killed as a result of these floods. So pretty dangerous and deadly. And China's had its share of death from floods. Very, very sad. I'm going to end today here with a flood of a different kind. An unusually hot January in 1919 created a situation where molasses tanks in an area in Boston burst. And this burst of molasses tanks, and we're talking like 2.3 million gallons of molasses, it caused a brown wave that was 9 meters high of this hot flowing molasses. And this wave killed 21 people. It knocked over buildings. It injured 150 more. It said that the molasses cooled very quickly and trapped people in the molasses. So rescue workers took hours to get people out of there. So you don't want to get caught in that kind of flood either. So that's it. I hope you enjoyed our lecture on rivers. Please don't hesitate to email me with questions, and stay dry.